approaches with machine learning methods. And currently, well, so usually machine learning overcomes the analytical approach. So what I say to my student is, so just take a machine learning approach first. And then, so if you are interested, then you can compare the performance with analytical approach. Well, so yeah, we can guess what happens in the futures. So in 2030, so in 5 years, wow, so there will be or almost perfect machine learning method. So if it's fixed, then yeah, just take this approach and that's all. Or otherwise, yeah, so I ask students to ask what kind of research topic you have to do is, so just ask ChatGPT like this. So, well, it's just joking, but anyway, so in this manner, so I'm gradually changing my mind and shifting to machine learning approach. And currently, much more interested in machine learning than analytical approach. Okay, so well, so I just briefly introduce what is machine learning. Okay, so the classical analytical approach. So usually we have a system. Okay, for example, digital filters or antennas, and input signal is also given. Okay, and what we want to see was output signal. Okay, the top figures. Okay, and the machine learning is completely different. Okay, so what we know in advance is data of input and output, the set of input and output information, and we don't know the performance of the system itself. Okay, and try to do training, and then the machine learning gives the best system will be this one. Okay, so this is how the machine learning works in the real world. So it's completely different from analytical approach. Okay, and there are two stages. One is training, and the other one is testing. So the training stage, so we have many, so huge number of training data. And usually, so in case of classification problems, the labels are already known. Okay, so we have input and output information. So input is image of apples, pears, and dog, cats, and the output is labels. Okay, so the name of apples, pears. So the input is image, and the output is label information. Okay, so then in the training stage, so just gives the input and output information, and so the machine learning algorithms, it takes image features. Okay, and so then so the final output we have learned models. Okay, so this is the outcome of training stage. So after that, we apply it to testing. So it's actual situation. So just put a test image. We don't know the label of itself, and try to guess what this image is. Okay, so we just using round model, and we can predict. So what kind of so what is this image? And then the estimation result is apple. So this is a way of machine learning. Okay, so so I'm introducing actually, so until now, there are so many different machine learning methods. Wow. Yeah, I just listed many different machine learning approaches, and they can be classified into, so in this slide, I classified into 4 categories. So the first one is supervised learning, and the second one is unsupervised or self-supervised learning. And so currently, the state-of-the-art technique is generative models. Okay. The first one, supervised learning, and you have already used, for example, gradient boosting. So XGBoost is a popular one for classification problems. And neural networks, convolutional neural network is also a powerful tool. And transformer is nowadays, so most of you are using ChatGPT applications. And well, so for my students, I sometimes ask, so what's the GPT means? What's the abbreviation GPTs? Okay, so here you see, so GPT is abbreviation of generative pre-trained transformers. So I mean, ChatGPT is one of transformer applications. Okay. And so for unsupervised learning, so autoencoder works quite well. And nowadays, generative methods are more attractive. So the GANs, generative adversarial networks, yeah, it works well. And so diffusion models is well, also a powerful tool to analyze so images and yeah, so many other informations. Well, so as I listed, so there exist, so currently there exist many different approaches and well, so what's important here is try to understand their features and for example, so for particular applications and yeah, we should know so which method is more effective, which method works well for particular applications. Okay, wow, so this is the popular ones. Currently, transformers and diffusion models, yeah, they are very much attractive in the real world. And well, actually, so because of limitation of presentation time, so I don't go to the details of these techniques, but well, so yeah, those two transformer and diffusion models, yeah, they are very powerful tool to analyze your system. Okay, and so wow, so yeah, so actually, so this is also what I said to my students. So what we will do in the futures, join industry or academies, and well, yeah, so you can choose so research on either core machine learning algorithms. Yeah, so some students say, so I'm really interested in machine learning itself. I mean, algorithms. Well, but there are many competitors, OpenAI, Google's, I say they pay a lot of money, I mean, $1 billion. And yeah, so I wonder if any of students can compete so with such a big guys, Google, Microsoft. And well, so instead, I usually recommend my students to do a research on machine learning applications. Well, so, so far, yeah, so here, today, many audiences are working in the field of antennas or microwave techniques. And then, well, so try to introduce machine learning to your research field. Yeah, that's the easiest way to introduce machine learning approach. Okay, so it's well, so yeah, actually, I'm working using machine learning, but I'm not working in the field of doing a research of machine learning itself. I don't. I'm just using machine learning as a tool written here, and so I'm just applying machine learning to actual research problems. So that's why many companies ask me how to use machine learning to this problem, this problem. So yeah, you can be kind of a consultant. So yeah, you can introduce this machine learning model will be suitable to your problems, to companies. Okay. Yeah, it works. And so yeah, so nowadays my students are joining industries and yeah, trying research on machine learning applications. Okay. So yeah, so the instead of core algorithms, I recommend to do research on machine learning applications. Okay, so from now, I'm introducing some application results of machine learning in digital sensing and applications in wireless communications. Okay, so in digital sensing, I'm collaborating with Murata Manufacturing. It's a Japanese company of millimeter wave radars. And also Nissan Motors. I'm not producing a car, but so those guys so asked me to how to judge connector fitting. Okay, so it's a kind of digital sensing, but you do not use radars, just core signal processing problems. But anyway, I'm introducing some application results in digital sensing. Okay. Yeah, so today I briefly introduce the topics. Yeah, actually I cover so many wide topics, and so I introduce each paper with just 2 or 3 slides. Okay, so what's radar-based detection? Okay, or recognitions. Yeah, I assume so the automotive radar applications. For example, so nowadays, automatic driving system is yeah, very much developed. And so for such purpose, so we have to detect the object or obstacles around the cars. Yeah, that's quite important task to prevent traffic accident. Okay, so actually, so around the cars, there are so many sensors. Well, yeah, you can imagine lidars or cameras and also millimeter wave radar. It works. Okay, well, it depends on situation. They have advantage as well as a drawback. Well, for example, lidars, yeah, it can detect the object very far from the car, but well, the view angle is very much restricted. Yeah, it cannot be 180 degrees. Well, for the cameras, yeah, so it's very accurate, high resolution. But in case of, yeah, for example, bad weather, I mean, a rainy day like today, or in case of a very dark situation in evening or night or early morning. Yeah, actually, so I went running this morning around 6 a.m. and it's completely dark in Kuala Lumpur. Okay, but anyway, so in such situation, the camera do not work at all. So instead, so millimeter wave radar works. It doesn't depend on such situation. It works in dark situation, and well, it can cover a very wide range, almost 180 degrees. Well, but the problem is actually resolutions. Well, but anyway, yeah, we can use millimeter wave radar. The frequency range is around 60 gigahertz or 70 gigahertz, and the bandwidth is around 4 gigahertz. Okay, so yeah, we can use millimeter wave radar. So outside of a car or inside of a car. So outside, we can detect object. So the obstacles around the car, and also the inside. So yeah, we can detect so child presence or adult presence. So in Europe, yeah, so they renewed their requirements. So this kind of so child presence detection system is mandatory in a few years. Okay. Well, so at the bottom right, yeah, you can see the actual photo of millimeter wave radar, Texas Instruments product. Well, this has 3x4, I mean 3 transmitting antenna and 4 receiver antenna, MIMO radars. Yeah, it works around 60 or 70 gigahertz frequencies. Okay, so using this kind of radars, yeah, so the first application is, yeah, so hand gesture recognitions. Well, it's a bit far from automotive radar, but yeah, so still we can use hand gesture recognition application to automotive radars. Okay, so the top left figure, the guys, yeah, so they are, they do not say bye-bye, but just shaking their hand and so try to open the doors without touching the doors, okay? So it's kind of touchless operations. Well, during COVID-19, okay, so this kind of touchless operations are very much widely used. Okay, so now, yeah, we can open the doors of a car without touching. I mean, just shaking hand and cars, I mean, millimeter wave radar recognize the motion of a hand. And then the door is automatically opened. Well, otherwise, so yeah, you can see the top middle figure, the car navigation systems. Okay, so in case of, yeah, of course, we often touch the screens. Well, but sometimes it may make a traffic accident. We too much pay attention to touching monitors. So instead, so just so we do not touch the screen, but just do yeah, so shaking hand or yeah, just turning your fingers, and then so the car navigation system it recognize your hand gestures and yeah, operate automatically. So nowadays, Google smartphones after Pixel 5, so they support well, so millimeter wave radars on top of smartphones, and yeah, they can recognize the kind of motions. Well, so yeah, of course, they have cameras, multiple cameras, and at the same time, they have an option of millimeter wave radars in the smartphones. Okay, so the bottom figure is an example of so how we can run and how we can estimate the motions of hand gestures. Okay, just yeah. So from millimeter wave radars, we can observe hand motions, and we can make so-called as a radar cube, the velocities and well, so angle, velocity, and range. Okay, so yeah, we put those information into a neural network model and then try to classify what kind of hand gesture is doing now. Okay, so actually, so for the details, yeah, you can refer those papers are already published. And wow, so in this slide, so this is actually the result of beginning of our research. Yeah, we did classification of 4 different hand gestures, hand motions. Well, yeah, you see the bottom figures. It's kind of movies, and so it's so radar cube, and wow, so for each hand motions, the radar information is quite different to each other. So try to classify the hand gestures using radar observed information. And yeah, we can use develop the so this kind of confusion matrix. And the success rate was around 97.8%. Okay, so at the beginning, well, we did a classification of 4 different hand gestures, and recently we have developed more complicated systems, tried to classify 11 different hand gestures. Okay, so as the bottom left figure, I show so the motion of hand gestures from top left to top right.
Dah potong dah orang tu depan ni dah. Dah potong dah pokok depan ni.
What does it mean? I see. Okay. Yeah. So can we proceed? Okay. Okay. So yeah, this time yeah, we classified 11 different hand gestures, hand motions. So in such case, well, of course, it's more severe conditions. Try to detect, try to classify. Yeah, actually, there are very similar motions, and to achieve high accuracy, so we did so a new approach of clutter removal. Okay, so yeah, try to detect yeah, so the vectors of clutter information and try to distinguish original motion and clutter motions. Okay, and well, so yeah, of course, this case we need machine learning again, and well, so the input information is mixed of real motion and clusters, and then machine learning, and the output is, I mean, so the test results so is the original, I mean, motion information without clusters. Yeah, it's achieved, and okay. Okay. Yeah, thank you. And yeah, so we can achieve smaller RMSE, means higher estimation accuracies. Okay, so this is overall of hand gesture recognition. And now I'm moving to next topic is so vehicle occupant detection. So this is so inside cars. So we detect so on which seat so child exists, or any adult exists, or no one exists. Okay, so in such case, so there exist many feature parameters. So the received signal power, or so yeah, for the power information, yeah, we can modify it into many different. I mean, so for example, maximum power and average power, medium powers, and their feature is different. So yeah, we try to evaluate so which feature parameter is more effective. To this kind of application. And well, so, and now, yeah, so we collaborated with industries, and yeah, so yeah, doing machine learning, we often use GPUs, graphical processing unit. Well, but we cannot install GPUs inside cars. So, so the industry company requires low-cost operation architectures. So for this problem, we simply used simple classification procedure, XGBoost. And so finally, we tried to modify, and so actually we tried to seek, looked for which feature information is more effective to this problem. And finally, we achieved the detection accuracy of almost 100%. And well, actually, so the XGBoost is a kind of a combination of binary trees. So in case visualize results, you see the bottom figures. So there are two examples of XGBoost output binary tree, approximate binary trees. Well, it looks a bit complicated, but it's just simple binary trees. So the computational cost is very small. And so, it's kind of, visible results. So which parameter, which feature parameter is more important, more effective to the output. Okay, so in this manner, so we developed vehicle occupant detection, and so actually that's already installed to radar systems. So it's again, it's also a different topic to ECG, electrocardiogram signal monitoring. Okay. So it's kind of to keep drivers safe health conditions. So usually to observe ECG signals. So we put patched, so connected sensors to our bodies or back. So, actually it's easy, but so the company requested us to use millimeter wave radar again. Okay, so the contactless signal detection or reconstruction. Wow, that's much difficult than connected sensors. Okay, because so radar receives signals are very noisy. And in case the radar is located far from the human means, okay, then it's really noisy. So instead, so just in this case, we installed a millimeter wave radar to a driver's seat, just the back side of drivers. It's just very close, but not contact. Okay. Well, it's around a 5 or 10 centimeters distance between the body and the radars. Okay, so anyway, it's a very noisy signal. And in this case, we adopted autoencoders and tried to reconstruct ECG signals. So in case ECG signals, okay, so the R peak, so-called R peak is very important. And so the interval between R and next R, so it's RR, it's called as RR intervals. So it's important information, and this case, so we we modified loss function using machine learning and reconstructed ECG and RRI signals. So we did we achieved very high accuracies. Okay. So even so contactless observations, very noisy signal, we can reconstruct the ECG signal very accurately. Okay, so so those are applications based on millimeter wave radar. And the next topic, connector fitting. This is I'm collaborating Nissan Motors, and it's not a millimeter wave radars. Actually, so their problem is in the factories. Yes, actually, so inside the cars, there are many connectors, many wires. They say so in one car there are more than 100 connectors, or more than 100 wires. Of course, the car parts of cars, so they are so made separately. For example, main bodies, windows, doors. So anyway, so many parts are connected by wires and connectors. Okay, so then, so what's the serious problem for car providers? So manufacturing companies, so the connection of wires. So it's really properly connected or not. Well, of course, so the experienced engineers, they judge if they are really connected or not. Okay, so based on their experience. Okay, well, but I should say it's a bit empirical. Okay. So instead, so we can evaluate the connector fitting in more objective sense. Okay. Okay, so just wear vibration sensors and try to detect vibration signal. Well, it's kind of it's same with microphones. Yeah, just put a microphone and record the sound of connector fitting. Well, it's kind of a very high frequency vibrated signal, and try to distinguish if the connector is appropriately fit or not. Okay. Yeah, of course, we can introduce analytical approach. Well, for example, using a spectrogram. Well, it's a classical way. Well, but so the achieved accuracy was not so high, around 90 or 95. And car company, so they are not satisfied with that result. Yeah, because so yeah, you can imagine. So yeah, just yeah, in one car there are hundreds of wires, and yeah, just one wires is not connected, and then car do not work. Okay, that's a serious problem for car product companies. Okay, so they need so the accuracy of almost 100%. Okay, so we introduced machine learning. So this time I introduced autoencoders and yeah, also transformers. But so far, transformer is not working well. So yeah, autoencoder is really a good tool for these applications. Okay, so we prepare the input data, I mean training data of so fit or not fit data and try to distinguish. Okay, using many different feature parameters. And finally, we achieved well almost a 99.7 or 8%. And well, actually, so now we are applying patents and well, so to develop the yeah, so the yeah, we can correspond to different shape of connector fitting evaluations. Okay, so actually this project is still undergoing, and we are now improving further using transformers. Okay, still we have time. Okay, yeah. So okay, so we are proceeding to applications in wireless communications. So I'm collaborating with KDDI research equipment. Well, so they are a second big company in Japan of mobile communications. Okay. Well, so toward yeah 5G and next, I mean 6G or beyond 5Gs. Yeah, there are many different topics. And yeah, so they are using machine learning already. And yeah, we pick up the yeah one topic, radio propagation prediction. Yeah, it's also important for wireless communication, mobile communication service providers. Okay. Well, so how the wireless communication is developed in these 40 or 45 years. Okay, so going back to 1980s, well, okay, so I'm still a primary school student, and that time, so we call it our first generation 1G, and so main purpose of application was voice communications. And then, okay, so we are moving to 2G, second generation, third generation, and fourth generation. And currently, we are using fifth generation wireless communication technologies. And how much the wireless communication speed is improved? Well, we may say more than 1 million times. Okay, yeah, it's a very big, huge improvement in these 40 years. Okay, and yeah, so you see application is changed, of course. Yeah, going back to 1980s, the main purpose was voice communication, and currently, so even in the wireless communication system, so we are watching hi-fi videos. Yeah, for example, YouTube or any other applications. Yeah, that's quite easy, and yeah, we need high-speed communications, even in the wireless situations. Okay, so now we are proceeding to next target, beyond 5G or with 6 generations. Well, to be the practical use in around 2030s. Okay. For such kind of application for beyond 5G or 6G, what is important for us customers and also for service providers? Okay, so for us, yeah, so the users, customers, yeah, we have mobile phones, smartphones. And what's the important information is, so which base station or access point is the best one to do communications. Okay, yeah, in case, yeah, for example, we may see or just we can receive several different signals from different base stations. And which one is best one to communicate? Okay, so this is a problem for customers. And on the other hand, for service providers, yeah, so in case the wireless communication speed is not enough, then they have to install new base station antenna. And then, so for service providers, which location, the important information is, so which place they have to install new base station antennas. Okay, yeah, of course, so they can do experiments. Yeah, for example, they have radar monitors and try to evaluate, try to measure received power, and then try to try to determine the location to install the new base station antenna. But it may take time. Okay, so instead, we can do such procedure by machine learning. Okay, well, so as you know, 5G and 6G, so one base station covers a very small range. For example, so in big cities, one base station covers only, for example, 300 meters diameters. And well, but we have to cover all the areas. And the problem is, well, so actually the propagation condition in cities, I mean urban district, is very much complicated because of many obstacles, high buildings, and there are many reflections, diffractions. And well, so in case of rural regions, local areas, yeah, just take so line of sight, and that's all. Oh, that's quite easy. But in urban district, well, I mean, yeah, for example, in the center, yeah, I was, yeah, last evening I stayed in KL Central, and wow, so there are many high buildings, and yeah, well, for the yeah, for wireless communications, it can be obstacles, and we have to measure, yeah, for example, reflection, diffraction, and so yeah, means so of course, yeah, usually we cannot see the base station antennas. So means the coming waves, most of them are so non-line of sight. Okay, so anyway, so it's important to understand such kind of wave propagation environment. And well, but it takes time if we do actual measurement. So instead of measurement, we try to predict. Okay, so the wave propagation conditions using machine learning. Okay, so for yeah, okay. So how the problem is how we estimate wave electromagnetic wave propagations from TX to RX. Okay, so currently, actually, there are many computer softwares like Wireless Insight. Yeah, they can do a kind of a ray tracing. Okay, so we can do a simulation how the waves, I mean, electromagnetic waves come from transmission antenna to receivers. And then, okay, so yeah, from you see the left figure, yeah, we can visualize the path. So which way the waves are coming. So yeah, of course, there exists a direct wave and reflection wave and some diffraction waves. Okay, and wow, so yeah, so this is a computer simulation results. Well, but for the service providers, they have to do measurement as well. Okay, so yeah, you see the right figures. Yeah, they install a measurement antenna on the cars, I mean, top of the roof, and drive along the main road. And actually it takes time around, so several hours, and try to visualize the measured results. Okay, the bottom right figure is that one. Yeah, you see the red region is strong power and green blue is weak powers. Yeah, it's a result of measurement. Well, but so yeah, as I said, so the actual measurement may take time. So instead of measurement, yeah, we can predict the antenna received power by using machine learning. Okay, so the problem is how to estimate the received power, or I may say path loss information. Yeah, so to estimate path loss or received power accurately. So what kind of information, what kind of features in machine learning is important? Well, so usually I may say, you see at the bottom left, TX and RX parameters. Well, yeah, of course they are very much important. TX height, TX power, gain, and the distance between TX and RX. Okay, so they are just scalar parameters, so we can combine them as just one vectors, and well, yeah, we can evaluate. We can put this vector as input of a neural network. Well, but so just 1D, one-dimensional information is not enough. So only with this information, we cannot achieve high accuracies. Okay, so we need more information. And what kind of extra information is, well, so you see the top left. Yeah, spatial data, two-dimensional data is much more effective. Just comparing 1D and 2D informations. And yeah, of course, now 2D information, yeah, we have plenty of knowledge. Plenty of information, much more information we have in 2 dimensions. Well, but for us, so we cannot effectively use spatial information. Yeah, for example, just aerial photos or building map. Well, but so we need some modifications. In case we do analytical approach. Well, but so thanks for the neural networks, machine learning. So just put spatial data as they are, okay? And then neural network, yeah, it's very wise. Okay, in this case, so the spatial data is 2 dimensions. So first we apply a convolutional neural network, which can deal with 2-dimensional information. And then so we put a 1-dimensional output and combined with TX, RX parameters. Okay, and then we put 1-dimensional information into a fully connected neural network, FNN. Okay, so we developed a combined model of CNN and FNN. And then finally, we have received power estimations, okay, results. And so, yes, this is the bottom right figure. This is a prediction result. Yeah, and predicted value is very much similar to actually measurement result. Okay, so we did some simulation on. Okay, so the top left figure is data set, and so red region is training data for training, and blue lines are used for test. Okay, and the measures data. Well, okay, so in this case, the top regions, it's a kind of a line of sight, and the bottom side is a non-line of sight. Okay, so the predicted error. Wow, so you see the bottom right figure. Okay, the white means so the almost zero errors. Okay, and red and blue is positive or negative errors. Okay. Well, but you mean so almost everywhere the result is almost white means the result is almost zero errors. So very accurate. Okay. So so the combined approach, CNN and FNN, so we can deal with both two-dimension and one-dimension informations. Okay, so we are now further developing this approach using different tools of machine learning. Okay, so this is a recent result. Actually, so 2 weeks ago, we gave a presentation of this result at the international conference held in Fukuoka in Japan. Okay, so what we did in this work was we are newly creating virtual 3D city map. So why we have to create a virtual 3D city map? Okay, so it's kind of an augmentations. Okay, so we have, so in neural networks, usually we require a large number of input-output informations. Okay, so using, for example, map data or measurements data. So what's the serious problem is to prepare a huge number of training data. Okay, so in this work, okay, so what's actual? Okay, actual, so usual, so yeah, we can use so limited number of map informations. Okay, so to prepare more and more map information, so we created virtual 3D city map using machine learning. And yeah, for this problem, we used diffusion model. So diffusion model is a kind of so creating something, any information from noisy input signals. So in this case, so we just prepare the noisy information. Yeah, you see the top left. Okay, so from a noisy image, we created the map information. Wow, so this is a test stage. So going back to training stage, yeah, we just did inverse from using information and try to move to a noisy image. Yeah, just adding more and more noises. Okay, so in test stage, we did inverse procedure. From noisy image, we can create novel the map image. And after that, we put a height information. Okay, so we developed 3D city map information and applying the wave propagation estimations. Okay, and it works. Okay, so we compare the performance. So using, we prepared 3 different approaches. The first one, generated 3D, is our approach. And the second one, simple model, is, it's a straightforward approach. Yeah, just prepare many rectangles and put many different rectangles and just consider it as a city map. Well, it's too straightforward. And the last one, Plato, is provided by the Ministry of Land Infrastructure in Japan. It's open source database and it's free. Yeah, you can use. You can visit this web page if you are interested. Okay, and many map information with height is available. Okay, so from using Plato model, we can create almost real the 3D city map and try to compare the performance. Well, until now, it's still undergoing project and the view is slightly different from actual 3D city map. Well, but for wave propagation estimation problem, yeah, it works almost similar to actual 3D city map. And we compared the performance, for example, path loss estimation, top right figure. And so the bottom right figure is, the horizontal axis is building occupancy, and the vertical axis is, path loss actually. So I mean, so these three approaches. Well, so at a glance, you may say, "Wow, it's wow, so miserable 3D city map." Well, because load information is difficult to deal with. So so at a glance, well, it's not good results, but it works for the purpose of 3D. So the path loss estimation, propagation estimations. Okay. And wow, so I'm introducing one more result, and yeah, so actually this is the final topic. And yeah, we also newly introduced a fine-tuning approach. So what's fine-tuning? Is well, additional tool in machine learning. Okay, so we are using transfer learning. Okay, so yeah, just imagine. So do training in big cities and do tests in a different city. Okay. Okay, so then the data for training and data for test are slightly different. The parameter feature is slightly different. Well, so even in central Tokyo's, okay, yeah, just divide into northern region and southeast region and southwest regions, and the characteristics are different to each others. Okay, so I mean, so yeah, do training using northern region and do estimation, do tests in southern region. Well, then the result will be not accurate at all. Okay, so in such case, so what we can do using the testing, training information in northern regions. So we can introduce a fine-tuning approach. Okay, so based on the training results in northern region, and just prepare additional information in southern regions. Okay, and try to improve the machine learning models. Okay, so slightly modifying by using southern regions. Okay, so it's possible, and yeah, we can apply this kind of approach to any different so applications. So in this case, we introduced a fine-tuning approach to wave propagation problem. So yeah, we did simulation in urban situation and suburban situations, and yeah, it works well. Yeah, so we did, so you see a fine-tuning approach. So for example, the left figure, you see the vertical axis is RMSE and how many fine-tuning layer is required. So gradually increasing the number of fine-tuning layers, and so the estimation error is decreasing. Okay, so but after a certain layers, the RMS is no longer improves. So it means so there exists so appropriate number of fine-tuning layers. So we have to detect such kind of information. That's important. But anyway, so we could improve the estimation accuracy by introducing fine-tuning, and we can reduce the estimation errors. Okay. Okay, so that's almost the end of my talk. I hope it's within the time. Okay. Okay, so just concluding my talk, I just introduced many different machine learning approaches. Wow, so I believe most of you are working in the field of antennas or microwaves, and wonders if you are already introduced machine learning or not. So in case you are still hesitating introducing machine learning, I may say, please do not hesitate to take machine learning. And what's important is now is, as I listed, there are many different machine learning approaches. And so what is, I recommend you is to know the feature of each machine learning algorithms and try to try to classify so which approach is more suitable for particular applications. Okay, so that's all my talk, and so this is a list of reference, and so thank you very much.
Thank you, Professor, for such a fascinating and insightful presentation on the integration of machine learning in sensing and wireless communications. So maybe we can have some few questions from the floor. Any questions?
Thank you very much. Very interesting presentation. So you explain many examples of that is possibly use the machine learning. So to understand the usefulness of machine learning, I would like to know the practical application situation of your each study that may be relating with some company request. So the connector matching seems practically now applied. So such example, please explain.
I see. Okay. Well, okay. Okay. Yeah. So thank you for the questions. Yeah. So as you stated, well, so there are many. I introduced many different applications, and for each applications, so different machine learning approach is suitable. And so what's important is, as I explained, so what kind of machine learning works or not. Yeah, try to detect. And well, usually we take trial and errors. And for actually these problems, yeah, first we used a transformer, but didn't work well. So finally we used autoencoders. And well, so autoencoders, so basically are developed for unsupervised problems. Well, but it works. Okay, so in such manners, so in this case, so we didn't prepare so many training data, and maybe that's the reason autoencoder works. So, well, so my answer is, well, yeah, we can, yeah, so as I stated, so there are many different, well, which one? Yeah, here. So far, there are many different approaches of machine learning. So try to detect, I mean, not only one, but yeah, you can apply two or more and try to evaluate which is more accurate. So yeah, that's important to apply machine learning to actual problems.
Yes.
Thank you for Prof. Ichige for the presentation. I can see many application can be used with the machine learning. But my question is that regarding the, like, for example, like path loss model for the EM propagations. Like this one, the next one.
Next one.
All right. So my question is that we have so many path loss model, right? So does the accuracy of the path loss model contribute to the accuracy of the machine learning? So is it better to choose much more accurate path loss model, a complex path loss model compared to the simple one? That's the question.
So do you mean
So-
so it works in a complicated situation or like a big city?
Of the path loss model, for example. So if more accurate path loss model, does it contribute to the much more accurate machine learning?
Yes, actually. So before machine learning, there exist many different approaches. So for example, ray tracing or empirical methods. Oh, so compared to those, I mean, analytical approaches, machine learning usually overcome their performance. And yeah, so we can further improve the performance of machine learning by introducing new techniques. For example, in this case, we newly introduced combined CNN plus FNN models. And then we can use two-dimensional information, as I stated. And then we can further improve the accuracies. And so yeah, it's applicable to analyzing big cities wave propagation situations.
Okay, thank you.
Thank you, Dr. Nurun. Is there any question? Okay.
Thank you for the great presentation. This is Samir from UKM. So we mostly use machine learning for prediction in our work. We work in antenna designs and wireless communication in general. So according to your experience now, how much the sample of the data that we need to get much more accurate results? Is there any threshold value?
Wow. Yeah, that's good. Yeah, actually, it depends on the applications. Well, but usually I may say several hundreds or several thousands. Well, but there is no any threshold or appropriate values. Yeah, usually I say, well, of course, so more and more training data, so we can improve machine learning accuracies. Well, but it's not becomes not suitable answers. Well, usually for many applications, we prepared around thousands of training data. And well, but sometimes it's difficult to prepare such a large number of training data. So in such situation, we use data augmentations. Yeah, so from using actual data and try to augment. I mean, prepare a different kind of data. I mean, try to increase the number of training data. Yeah, for example, yeah. So in case of image, digital 2D informations, yeah, just taking this area, or but in case we permit overlapping to each other, then we can increase the number of informations. So for example, in such manner, so increasing the number of information is really important. And so the virtual data, well, for example, well, this one, yeah, so this is also to increase the number of data. Okay, so well, yeah, going back to your questions. Okay, so usually we may say so several thousands of training data will be okay, and but it depends on situation. So you can do training and test and see the test results, and yeah, and then you can evaluate if it's okay or not. Okay.
Thank you. Any question? We have some 10 minutes left.
Okay. Thank you very much, Sensei, for a very interesting introduction to machine learning, especially for people like me who's not in machine learning but try to jump into machine learning world. So for someone like me, actually, this is the extension of the Yamada Sensei question. I believe you already answered that we have so many learning like SG Boost, so many. So when I'm still new and I'm trying to pick which one is better for this my research problem. So do I go for just like do research and then fix with one approach, or maybe do use like 3 approach and then compare the result? What is your opinion and advice on that?
Okay. So depending on the problems, but well, for antenna designs, so you know now, so there are many classical or so highly experienced engineers developed very good ways, and so I'm not sure if machine learning works for such kind of already developed applications. Wow, so all the applications I introduced today is wow. So analytical approach do not work well. So I newly introduced machine learning and it works well. Wow, so depends on the problems. Okay, but wow, so introducing machine learning and you may find so different point of view from a classical approach. Yeah, that's a good point. And so then you can find any new novel classical analytical approach as well.
That's okay. If there is no question, we can proceed to the next speaker. Thank you, Prof, for your presentation. Next, we are honored to have Professor Technologist Dr. Mardeni bin Roslee, Professor at Multimedia University, Malaysia. He will be sharing on the topic AI in agriculture, why and how. Please welcome Professor Emeritus Dr. Mardeni Roslee.
Bismillahirrahmanirrahim. Kena eh? Alah, Okay. First of all, on behalf of our faculty and also university, welcome to MMU. I believe maybe some of you, yeah, maybe this is the first time coming to MMU and first time coming to our faculty. Yeah, so welcome, especially our keynotes and also the members from Antenna and Propagation Society. I am from Comsoc, ATB Comsoc VTS. I was the chair for this chapter before. And maybe perhaps I will join APT, Antenna Propagation Society, for next AGM. Okay. Again, so thank you very much lah, and well done for our organizer organizing this forum or maybe sharing sessions. It's good for the chapters and also the community under microwave antenna propagations, and also, of course, to our students. And I believe maybe some student, not only from MMU, maybe from UTM, UITM, yeah. And we have Dr. Samir from UKM. Welcome. Okay, berapa lama? Setengah jam Okay, I'm Mardeni Roslee. I'm from Center for Wireless Technologies. So I believe we have a very strong committee from this chapter, Dr. Nolinda. He's also under the same research center with me, all right? And we are under the Center of Excellence Intelligent Networks in MMU. Okay, and also I'm representing Academy Science Malaysia, SM. And Shongwa for today, I think since all of you come from different background, maybe I try to simplify my presentations to make everyone can understand about these things. Just now we have our first DLP speaker talking more on this machine learning, right? So it's quite famous and quite important, especially in Asian country. I believe Japan, Korea, and China, they are really strong in these keywords, AI. So for Malaysia, we also adapt these technologies to our community. So our government really support this AI come to us. Even we have AI frameworks, AI blueprints under our governance. So my topic is quite simple. Is why and how on the AI. I think everyone know what's AI. All know what is AI. It's for everyone. Artificial intelligence. And our faculty, we just rebrand to AI faculty just this year, launched by our Prime Minister, Anwar Ibrahim. And a lot of application for AI. Okay, and for my sharing session today, I would like to share on this AI apply in agriculture. Maybe this morning's everyone's you took your breakfast. Maybe there are some fruits, maybe vegetables. I guess lah outside nasi lemak. So it's about the vegetable, it's about the fruits. So I mean it's our daily foods that's we must have as a human for the healthy. So because of this agriculture, I mean more deeper one is farming. Is very important for the nation, and today what we have is so many traditional methods. So that's why in these projects I work with Semdarbi plantations. Okay, solving the problem on the agriculture. Okay, so it's about the why and how. Kenapa and bagaimana. Okay, before I start, this is just a very welcome to everyone, Faculty of AI Engineering. Okay, and we are AI. Our faculty, we are very support AI. Okay, under our research center, we have a few domains that we focus. Okay, I believe we have around 16 to 18 members under our research center. All right, and we are focusing on some domain here. For example, 6G, IoT, UAV, antenna. Even antenna is also under our research center. Okay, and radar, satellites. Okay, and many more. So we are working on these cross disciplines for the domains under wireless technologies. So, so you're welcome to collaborate with our university. So this is our main domain, and we have strong support from government, industries for the collaborator and also the funding. Okay. We were talking about this before I go to AI in agriculture. Okay, let me talk on this precision agriculture. What is a precision agriculture? So I believe we need AI in every sectors. For example, in factories, in logistics, we need AI. For what purpose? Replacing the human. So in agriculture, we need AI for three purposes. Okay. So number one is monitoring, to monitor. Okay. Number two is a predictive analysis. And number three is of course the solution. Solution means decision making. Means that the farmer, the traditional farmer, not required to go to the site, okay, and do some traditional methods in doing a monitoring process. So what's this precision agriculture have is everything is robotic. So how we can implement this? That's why we need AI. So we start from this video. Okay. So we know the vegetable, the fruits, consider our daily food. I believe later on lunch we have maybe fruits, maybe vegetables. So we need a human to monitor very proper. Okay? Or else they have a lot of problems come to this plantation or the farming or agriculture system. It will cause the low production. I mean low productivities. Okay, that's why we need some technologies replacing the human in the agriculture. Okay. Okay, we're talking about the agriculture. It's very broad. In Malaysia, they have a lot of estate. We understand. So, for example, Sam Darby, we have around 200 plus. I can say he is palm oil mills and around 600,000 hectare in Malaysia and some other countries. Okay, Sam Darby plantation. It's a very big company in doing this agriculture research. Okay, so meaning that agriculture is considered the main source of our we also have in some areas like Sabah and Sarawak. That's why these have become very important for Malaysian as well as ASEAN people. So for the information, like for example in Malaysia we have I can say 2 seasons. Is raining and dry. We only have these 2 seasons. So means the water table will be fluctuating. Can be high, can be low. So to get the optimum is very, very difficult. And to achieve the optimum, so we need the proper monitoring system. Okay. So what we have today is a traditional farmer based on the experience. Go to the site and monitor this fluctuation of this water table, the purple layers. Okay. So do you know what's precision agriculture? What does it mean by precision here? I mean we need more accurate result based on the predictive analysis, and we need the correct decision making. So that's why we need AI. AI will help these technologies, agriculture in making the right decision making. So for example, the solution. Okay, so this is the meaning of the precision agriculture. We need more proper monitoring system and proper solution. Okay, we understand this precision agriculture is not only required in Malaysia, also in some areas. Okay, I just come back from Japan and also China last 2 months. So they're very rich with AI, especially on the robotic side. So over there, they use AI and robotic system in all the plantation areas. In Malaysia, we are slowly moving to these technologies. So what you can see, basically the farmer, what they want is the outcome from the mapping of this technology. So it means the farmer know which area having a maybe below the optimum or below the threshold for the parameters. For the information, just now I only show the soil properties. One of them is a water table thickness. Actually, they have a lot. For example, the soil temperature, the soil moisture, the soil pH, and many more. That's why this farmer, they need these informations for them. Then they can monitor regularly in all the estate in Malaysia. Okay, so we need the farmer need this. Unfortunately, not all the rural areas. Normally, this agriculture and this plantation area, we can see at the rural areas, kawasan pendalaman. Unfortunately, the signal probably not good as we expect in the rural areas. That's the challenges in Malaysia. Okay, so just want to compare Malaysia and New Zealand. New Zealand, even in the forest area, over there the signal very, very good. Kat Malaysia hanya bandar yang kawasan-kawasan yang padat penduduk, we can get the better signal. Dekat sana hutan, kita boleh capture the signal. So means whatever animals there, we can monitor. Dekat sini kita tak boleh monitor the animals. Animal akan makan kita. Contohnya gajah, monyet semua, difficult to monitor. Kalau for example, the elephant, they want to destroy this tree just now. So how we can fight with the elephants? Cannot. Over there, they have a monitoring system, robotic. Not to kill the animals, just to minimize and avoid these animals come to the plantation and damage their crop. So that's why we need this AI in agriculture. Okay. Previously, we have some discussion with these 2 companies. The first one is Tabung Haji Plantation, Berhad. Okay, second one is the SEM derby. To identify what was the problem statement, actual problem statement. Okay. So this problem statement is happened many years. Okay. And to adapt our robotic AI come to us is very challenging. It's because in Malaysia we have difference. We have a different geographical and different weather. Kita hanya ada dua, hujan dan panas. It's very different. If a temperature like dekat Cameron, Bukit Tinggi is good. But in Malaysia, not all the areas, not all the estate. We are having the weather like Cameron, Genting, Bukit Tinggi, tak semua. Contohnya dekat Nilai, for example at Nilai, very hot and sometimes raining. So it's very challenging for us to monitor. So what was the problem statement? They use a very traditional method. Okay, they use a traditional method in monitorings. I can say the soil properties. Like human, we have to monitor more regularly our heart, right? Because all the disease come from the heart. If your heart not properly working, it will affect everything, your movement. So for plantation and agriculture, the heart is the soil. So I mean, if the soil not good, not optimum enough for all the parameters affecting the crop management, so definitely will affect the productivity. All right. So what was the problems faced in this technology? They use quite traditional methods. So for example, here they correct out the soil sample and then bring to the lab, getting the reading and give decisions. So making a delay for these methods. So because of that, we are from engineering. For example, me, I'm not from agriculture. My degree not in agriculture, but I work with agriculture to helps and collaborates with the agriculture community. So we have AI, and we understand AI is cover everything. It's not only for agriculture, actually it's for healthcare, finance, transportation, entertainment, everything. So it's very simple to say, for example, very obvious I can say it's healthcare medical, the doctor, medical doctor, they only they use this AI to give the decision on how to treat their patient, which solution, which medicine, which kind of treatment, what level of treatments, everything is decided by AI. And plus the experience of the medical doctor MO. Okay. Similar with agriculture. So what's we have a very experienced farmer, we have a very experienced supervisor, and we have a very I can say very sophisticated tools, software, but still have a lacking in terms of the monitoring and also decision making. That's why this AI consider is the best platform. Okay, just now Prof. Koichi, you have explained about the machine learning. It's a very interesting to learn about the machine learning. My team also, we work on the machine learning on the so many applications. It's not only agriculture, it's for wireless communication, 5G, 6G. And you have AI, and it's very common. AI will pass IoT. So IoT is for everyone. It's one Internet of Things. Internet for everything. For smart agriculture, we use this AI, we use this IoT for a lot of applications. One of them is the UAV. What UAV is like the drones. Drones. Kapal terbang kecil, drones. And we use this AI for other purposes like monitor the forest. hutan, especially kita nak jaga hutan, we want to minimize binatang buas from damage the trees. And this IoT in agriculture is used for aquaponics. Nak jaga ikan. We want to maintain the fish quality because fish for everyone. Every day we eat the fish. They consider very high protein. Batuk lah ada. Nak minum kopi ke? Okay, for aquaponics, to monitor the fish. So the businessmen, they use this AI in agriculture in monitor the fish for aquaponics. Others, like you mentioned, you use this IoT for monitoring the farm, estate, farming, and in Malaysia, palm oil. Is there any palm oil at Japan? No. So not because of the different weather, because of different soil types. In Malaysia, we have 7 soil types. So in Japan, they have different soil types. That's why palm oil is only suitable in Malaysia. Okay, other than that, UAV, yes, Japan, they have a lot UAV in monitoring this farming. Okay, especially in the Tokyo area, in the rural. Tokyo, they have 2 parts, city and rural. So this farming, they use at the rural areas. Okay, I think it's very common for everyone. Unmanned aerial vehicle. Okay, ataupun in bahasa is kenderaan aerial unmanned. But human cannot use this to fly. So human use this for what? Monitoring, do mapping, do scanning for a lot of applications. So one of them is we use this UAV in wireless communication to extend the coverage. It's like the base station. Today what you can see, base station is located beside the roads, beside the hills, the high tower. That one is a fix. What happens if the signal is not covered for certain areas? That's why we need this UAV in extending the coverage. Where we don't need to demolish the existing tower. For the information, in Malaysia, one tower, it costs around 80,000 Malaysian ringgit. And a lot of operators, they are installing their antenna dekat base station. Mardeni, they are very strong on this base station projects. So this unmanned aerial vehicle considered is the solution because this one is moving to extend the coverage. In agriculture, we really did this. One thing is because the estate is large. So it means instead of farmer moving from one side to another side using maybe motorbikes, maybe the plantations vehicles, why not using these technologies in doing the large estate, the large monitoring areas? It's good for them. So this is only to extend, to do a mapping, to do the scanning, and the human can see from the single station. So that's why we need this. Okay, from the problem statement, from the technologies, now I can say all in one is become the AI in agriculture, meaning is what? AI combined with IoT, combined with UAV. So these 3 technologies will be merged together in solving the AI or in solving the agriculture problems. And we need AI for three purposes, like I mentioned. Okay, monitoring, analysis, and decision making. And then we need IoT is because the IoT devices will be placed at some points of your areas to give the reading to the farmer at the control station. And then you need this UAV because this UAV is not fixed, it's moving from one small area to the other areas. So it's good. So so this is the solutions in agriculture. Okay, the question now is, do you know in implementing AI in agriculture, there were some methods available and some new methods that this AI introduced. Okay, so what you can see here. So as I mentioned, the soil is the first thing that we should monitor. Okay, so AI in agriculture will give the reading for the soil properties. So one of them, as I mentioned, we have a soil temperature, soil moisture, soil pH, and everything. And especially the health of this crop is because sometimes the animals and also the insects will damage the trees, and then it will affect the crop. So tak bagus lah. So means we need to minimize this. So UAV will be used to identify, to spray the location. So this insect dia akan lari lah. So in order for us to monitor, I mean the farmer, to monitor this very large estate, just use the single device. Okay. And again, as I mentioned, in Malaysia, palm oil in the rural areas is the first challenges for us. And this smart farming apps will not only monitor using this UAV. Actually, they have autonomous robot, especially in giving the optimum nutrients, optimum water level and everything. So, so for example, we have this autonomous robot in helping using this AI and spray this effective area. Some areas they identify lack of water table, not really moisture enough, and some areas they are too much, too maximum. That means not required to spray. So only the effective area they will these autonomous robots will spray in order to give a very optimum crop. And we need the big data. This is the big data. This big data we will apply by the farmer. Okay, we apply by the farmer to give the decisions. Sama ada nak lebihkan nutrients or maybe more water. It's because this is the only solution, especially in Malaysia. We cannot control the weather. Weather control the human. So the third application of AI in agriculture, what you can see here, as an autonomous robot. So the autonomous robots will go side by side. Will monitor area per area. In giving the decision on which area must be sprayed, must giving more nutrients in order to provide the optimum crop. This is happen, and it's obviously you can see here. Two vehicles will work. One is a UAV, Second one is the autonomous robot. Okay, and this technology is important in agriculture, and we need AI We need AI in helping us on this. Okay, basically this AI, this is a smart AI agriculture, use IoT, use AI, use AV, okay, to increase the efficiency, sustainability, and higher yields. That means optimum crop. So maksud dia, the soil become more health. Right? Enough, like human, we need enough water in our body. If lack of water, so it will affect our body. So for nutrients, for the soil, so also require optimum water levels for the soil. And these are I we use in agriculture for, as I mentioned, is decision makings. So for example, soil management, crop, livestock, precision irrigations, okay, and automated machinery like autonomous robot I showed just now for weeding, planting, and investing for greater precision. Okay, like everything done by this AI, so the farmer will more relaxed and more smart. Okay, there are four basic methods on how we can apply in a agriculture system. Okay, number one is of course data collections. So the data collection will involve the sensor. Will place the sensor in some areas in the estate. The data collection we use this sensor UAV and of course GPS to do the mapping. Okay, in order to monitor this reading. After data collections, we need to do data analysis. So AI will do this. AI and machine learning will analyze this big data to identify the pattern. This pattern is very important. The farmer, they need this pattern. Okay. And then intelligent decision making. This one we need algorithm. Okay, to provide the recommendation for everything. So for example here, fertilization, watering, and other interventions. And we need this decision making. Okay, this is good for AI. It's not only detection, it's decision making. Like our faculty lah, it's not only detecting which program is the good, we also provide the solution for our future students. And that's why it's good for the PG student, postdoc to join us lah in our faculty. Automations, we have this one is more to the autonomous robot, like I mentioned. And then we use robotics technologies to perform the tasks like precision and increase the efficiency. Okay, basically these are four things that we must apply in the AI agriculture. Okay, data collection, analysis, decision making, and automation. In other words, automation is the last thing lah. Last thing. Example is the UAV, which area should be provides more water. Autonomous robots will automatically provide the solution, which soil need more nutrients and so on. Okay. Let me talk about one of our previous projects. Okay. I think this is more to wireless communications. We use again IoT, like I mentioned just now. Okay, and we design LoRaWAN. LoRaWAN is the long range wide area networks. Okay, what is LoRaWAN? It's a long range, low power data transmissions. But in rural areas, we really need low power data transmission. Okay, and what is our target? Okay, they have 4 parameters we focus. Okay, there are 4 parameters that we focus. Number 1 is the soil water table. From time to time, we can see how it's fluctuating. Okay. Okay. Number 2 is the soil temperature. from time to time, we can see, we can monitor, is running from low to high temperature. Of course, weather temperature is different with soil temperature. Dekat atas line, bawah line. And then we have a soil pH. Like for chemistry people, they know what is the optimum pH. For this one, the soil pH is around 6 to 7. Okay. And also this soil moisture, kelembapan. Definitely, if the soil have more water, so it means consider more moisture, or we can say moisture enough. This is the purpose of this AI agriculture. So we have LoRaWAN is monitor to parameters, including this water table, and then it consists of few components. Okay, so for example, we have LoRa wireless module, transducer, sensor, and okay, these components. Okay, we have this pipe will be attached to the palm oil trees, and then the sensor will detect the reading, and then will provides to this gateway, okay, and go to the networks and application server. Okay, at the ends, we can easily monitor the reading from the single device. Okay, so this is the design. So basically how it works, so you can see here, for example, this one trees. Okay, we place this sensor for one trees. Okay, so for example, in Nilai and Carey Island, they have some power areas that require very minimum IoT sensor. That's why we no need to put sensor for every palm oil trees. It will cost. Right? So it's because this sensor will only detect few coverage. So I mean it can cover around 50 to 60 palm oil trees. And then for the large areas, the signal will be extended by LoRaWAN, long range wide area networks. Okay, so this is how it works. And again, this is the autonomous robots based on the this AI decision makings. So these autonomous robots will move from one side to another side. For example, providing small water for the soil and the nutrients for the soil areas. So this one considers the robotics replacing the human. We as a farmer, so this is the farmer, just monitor the parameters from the single station. So okay, this is the one of these the autonomous robots. What actually the outcome we got from the single device? Okay, from the mapping, you can see they have a few dimensions come together with a few parameters readings. Giving the, this is considered a predictive analysis. Giving the farmer to decide what is the solution. So for example, we got a few colors here come together with different soil water table contents. Okay, and then at the same time, we can see from our these four parameters: water table, moisture, pH, and temperatures. The reading for every parts of these effective areas. Okay, this is a top view. It's not only a top view, and this thing can see from the side view. That means it's a 3D. Because in under the bottom of this soil, they have so many layers. But we only want to focus on the top 5 centimeter depth. Okay. We understand, for example, in Malaysia, not all the areas are considered effective areas. Contohnya dekat sini So the effective areas only this part. This one maybe the jungle or the forest. So we can scope our areas, okay, and the forest which doesn't have the palm oil or maybe the fruits trees, we not require to do this AI predictive analysis. Okay, so men can focus on the certain areas. Okay, again, from this mapping, okay, the farmer easily can give the decisions about. You can see this part, maybe this one, the optimum is in the middle. So how much percentage lacking here for this centimeter, and how much this soil water, this soil moisture, soil pH, and soil temperature require. So, for example, in this case, the soil water table not reach optimum. Soil temperature not reach optimum. Maybe this one during the dry season, musim panas dekat Malaysia. Bila musim panas kat Malaysia? My friend from Japan, they asked from January to December, which month is the hottest? I can say every day is hotter for me. Tak tahu bila Every day is hot for me. And sometimes raining. I also don't have the answer. When is the raining time in Malaysia? Mungkin December lah. Especially in Pantai Timur, Kelantan, Terengganu, all akan banjir. So in Malaysia, this climate changes is very, very challenges for the farmer. Not like other places, especially Japan, they're very cool everywhere. Everywhere cool. So mean the crop is optimum enough everywhere. Okay, and we are applying this IoT, we are applying this UAV, okay? So we relate with the theoretical parts, this more IoT nodes we will place on the some palm oil trees, and then they will giving a better result. Okay, why? Because this LoRaWAN helps this farmer to extend the coverage. Okay, and from time to time, this is the actual reading taken. So the soil water table will be reduced. Okay, especially during the we have 24 hours one day. We got 0 to 12, 12 to 24. So this one will reflecting. Will be increase, decrease, increase, decrease, and the maximums we can see, at the 3 p.m. 3 p.m. time. So means the good time for palm oil for better crop in Malaysia is around 3 p.m. Not in the morning or not at night time. 3 p.m. is the best time because that time is the good. Is enough moisture, enough temperature, enough pH. So that's why we can easily go and monitor traditionally, but here not traditionally using AI. Okay, again, this AI agriculture is about technology, right? I mean, we are engineering, we are helping these different domains. This one is agriculture. We also work with veterinary groups, and what you can see here is really making better GDP for our nation people. From time to time, from year to year, you can see it's an increase. So means for the young generation, for our students, don't worry, AI will work with us, and you will get better AI opportunities to work in some industries Okay, so it's really making a high economic impact. Why? It's because productivity. Okay. Okay, so again, this AI agriculture, I can say it's very useful, obviously very useful. Optimize the smart system. Definitely smart system. Actually, Malaysia, we want to make this a smart agriculture 100% come to us. Like New Zealand. New Zealand, we understand, less people, more robotics. More peaceful. That means when our people working there, you can see this thing happen. More technologies, less people, more cooler, and very peaceful place. And our method is patented under this MyPo. Okay, thank you. And again, it's sponsored by international funder. And alhamdulillah, we got some recognitions on our methods from, thank you, Japan. The award from Japan. I don't know what's the guy's name here. Okay, thank you. Okay, so conclusions. AI, we know is for everyone. And now AI will helps the human, not making the jobless for the human. Actually, it's making more jobs. Why? Because AI they have a lot of chunk. We got machine learning, we got robotic, we got deep learnings, we got the computer vision, everything. So our student can try to adapt at any of the AI sub technologies here. Don't think that's when everything is robotic, no job for our student. And that's not correct. So actually, it's making more jobs. As I mentioned in the market analysis just now, it's increased. The job opportunity will increase. Again, those interested working in agriculture, so you may looking at opportunities to work on AI in solving this AI problem. Okay, so this is my conclusions. Again, on behalf of our research center, on behalf of our IEEE Comsort VTS, and also our Faculty of AI Engineering. Okay, thank you very much for your attention today. Okay, and yeah, for any questions, so I pass to Mr. MC. Okay, thank you very much.
Okay, thank you, Professor, for the engaging and informative session. So as we ahead of our time, maybe one question from the floor.
Lebih masuk
Thank you, Prof. Mardeni. Inspiring presentation. I would like to know, I'm not sure whether this one relevant or not, but I would like to know how the knowledge from your research has been transferred to the farmers. So for example, they're very digital divide between researcher and farmer. So based on your experience, do you have any how do you have conduct some workshop or something like that?
Yeah, good
Thank you.
question. Yeah. Okay, actually, when the problem statement not from university, normally the problem statement from industry. When the problem statement come to us, the first thing what I and my team did was we become the farmer. Saya jadi pekebun, pekebun, bukan inilah pekebun. So the farmer go to the site, getting the experience how to traditionally monitor the areas, the soil property, the trees and everything. From there, we identify some important parameters, apply into the AI, especially our robotics and UAV on the machine learning part. How this thing, especially from the big data, can be translated into the farmer required information. So the farmer, they can know lah. So for example, as mentioned just now, we have a certain areas. This is the forest. Okay, and then this is the palm oil areas. So we want to focus these areas. What you can see, yellow, red, green. So yellow means is a optimum soil water table. So I mean maybe it's around 6 centimeter. So as mentioned, minimum is a 5 centimeter depth. The rest is too low. So for example, red one is I remember this one is around 1 centimeter. Even the areas is not big, but because of the Malaysia climate changing, so it will affect the whole areas. And this part is not because of the weather, it's because of the soil quantity and also the soil quality. Even these areas using the same soil type. As I mentioned, in Malaysia, we have 7 type of soil. So this is the effective area. So the farmer, they happy because they can detect, they can monitor these areas, which area less water, which area less temperature. The rest, they don't need to focus because it's not their area. Okay, good for the farmer lah. So farmer tak perlu pergi site lah. And they just focus this part. And then this one in a single big screen lah. Dekat the control station. That's the contribution from AI to farmer lah. Yeah, maybe I answer your question or okay.
Okay, thank you, Prof, for your session. Before we proceed to next speaker, I would like to invite Prof Yamada, followed by Associate Prof Dr. Kamila Kamadin for token of appreciation.
Okay, thank you very much.
Yes, okay. Thank you, Prof. Okay. Our next speaker is Associate Prof Dr. Shah Alam from University Trisakti, Jakarta, Indonesia. His topic today is integrated microwave sensor with antenna for material characterization and data transfer capabilities. He will present from our online session. Please welcome Associate Prof Dr. Shah Alam.
Okay, thank you. Can you hear my voice? Is it clear?
Yes, clear.
Okay, thank you. Okay, I will share my presentation. Okay, can you see my slide? It's okay. Okay, thank you for the moderator. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen, and all the participants from Antenna Propagation Technical Series 5, 2025. I'm Associate Professor Dr. Syah Alam from Department of Electrical Engineering, Universitas Trisakti, Jakarta, Indonesia. In this session, I will deliver my presentation about the integrated microwave sensor with antenna for material characterization and data transfer capabilities. Okay, before I start my presentation, let me introduce my university. This is the profile of our university, Universitas Trisakti, founded on November 29. 1965, established by government in the first president of Indonesia, Insinyur Soekarno, and the location of the main campus is in the Kiai Tapa Street, number 1, Grogol, West Jakarta, Indonesia. And Universitas Trisakti has more than 18,000 active students and has graduated more than 100,000 alumni. And we have 9 faculties: law, economic, business, medicine, density, civil engineering and planning, industrial technology, earth and energy technology, landscape architecture and environmental engineering, and also art and design faculty. And we also acknowledged by QS and World University Ranking. And we also has institutional accreditation awarded by Indonesian National Accreditation Board of Higher Education in the excellent. And this is the location of our main campus. So if you go to Indonesia, maybe we can discuss, or maybe we can collaborate in research, or maybe education, mobility student, and so on. Okay, this is my short CV. I finished my Bachelor of Electrical Engineering in Universitas Pendidikan Indonesia, West Java, and I continue my Master of Electrical Engineering at Universitas Trisakti. And in 2024, I finished my PhD in Microwave Engineering at University Technical Malaysia Melaka, and this is my teaching experience. From 2014 until 2018, I appointed as a full-time lecturer at GTA 45 Jakarta, and 2019 until now, I am appointed as an associate professor at Universitas Trisakti. And this is my profile from Scopus, Scholar, Sinta portal, and also Web of Science. Okay, this is the outline of my presentation. First, we discuss about the microwave sensor, and then we move to the basic concept of material characterization. And then we discuss about the fundamental theory of the resonant perturbation, because if we design a microwave sensor, if we want to detect the permittivity or maybe permeability of the material, we can use the resonant perturbation. And then the application of the microwave sensor, and then the research gap in opportunity. And we also explain about previous research that had this from our team. First, dual band independent microwave sensor, and then integrated microwave sensor and antenna sensor, multifunctional dual band microwave sensor and antenna, and then dual modalities microwave sensor for contact and contactless detection. And the last project is a high stability microwave sensor based on IDC structure with dual band branch line. And also we present the future work of the microwave sensor. Okay, first, we must know about what is the microwave sensor. Okay, the microwave sensor is an electronic device that detects and characterizes the property of materials such as motion and temperature. And we can see in here, this is the example of one of the microwave sensor that has been designed. We used a simple T-stab resonator based on microstrip. And then we place the sample. We can see in here, this is the material A. This is for non-contact detection. And this is for the contact detection. And this is the response of the resonant frequency after we place the sample in the sensing area. And the microwave sensor also operate at a different frequency within the microwave spectrum by interacting the electromagnetic field with the tested samples. We change the response behavior of the sensor. This is the basic concept of the material characterization. First, we can determine the sensing area of the microwave sensor based on the electric field concentration. So in our research, we focus to detect permittivity of the electric materials. So we can use the electric field concentration that can interact it with the sample. So the resonant frequency after we put the sample in the sensing area is moved to the lower. So this is the illustration of the electric field concentration of the dual U-shaped resonator. This is my first project. Okay, and this is the scenario where we place the sample or the material under test. So we can place the sample based on the maximum electric field concentration of the resonator. And after that, we can analyze the permittivity based on the shift of resonant frequency of the resonator. Okay, this is the classification of material characterization method. Okay, material characterization technique have been developed in the recent years. Various techniques are available for real part measurement of the complex permittivity. For example, for the electric constant. And each technique is useful for certain materials application at certain range of frequency. So we can separate the material characterization method into two different kind method, resonant method and non-resonant method. The non-resonant method over the frequency range can be used to determine the electromagnetic properties, while the resonant method gives more accurate knowledge of the electric over a certain frequency range or single frequency. So in our research, we propose the resonant method with the resonant perturbation theory using planar microstrip. Okay, so we use a single port resonator, can be function as a microwave sensor and also can be function as an antenna for data transfer capability. And this is the fundamental theory of the resonant perturbation. As we know that the perturbation is caused when the material under test is introduced into a microstrip resonance structure. And the interaction of the material under test and store electric field energy changes the resonant frequency from where the electric properties can be evaluated. So we can use this general formula for perturbation theory. And this is the illustration, the simulation result from the SFSS. We use SFSS to analyze the location of the sensing area based on the high concentration of electric field. You can see in here the maximum of electric field in the left arm of the first U-shaped resonator, and in other resonant frequency, the maximum electric field in the left arm of the second U-shaped resonator. So we can use this phenomena to determine the sensing location, so we can place the material under test based on this simulation. And this is example for the measurement setup. We use a vector network analyzer, and we connected the resonator using a coaxial cable, and we use dielectric materials with known permittivity such as RO 580, RO 4003C, and Evercore. And this is the perturbation theory. Referring to perturbation theory, it's clear that the change in permittivity of the material under test is in line with the changes in the resonant frequency. When the material placed in the sensing hotspot area will perturbate the fields. We also analyze the parameter of the sensor such as a sensitivity and normalized sensitivity. Sensitivity is represent the ratio between frequency shift and the change in permittivity. So we can use this general formula, and after that we also analyze the normalized sensitivity with this general formula. Okay, this is the general application of the microwave sensor. So we can use the microwave sensor for material characterization, such as for the industrial quality control, moisture sensing, chemical and biological sensing, and also for the temperature sensing. In our research, we focus to use microwave sensor to detect permittivity of dielectric properties. Such as maybe in this evening, my student will present the material microwave sensor for vegetables material characterization. Okay, and this is the specific application. We can see there are a lot of applications that we can integrate or we can use for a microwave sensor, such as position, proximity, vibration, acceleration, okay, chemical, flow, humidity, moisture water, same that present in the last previous speaker. Okay, and then this is one of the example integration between the microwave sensor with the IoT device. So we can see this is the microwave sensor. that used to detect liquid under test, and after that the microwave sensor connected to the RX and TX antenna, and after that the data from the measurement can be transferred using Wi-Fi and can be accessed using internet. This is the recent development of the microwave sensor. So most of the researcher, if we read the paper from IEEE or another journal, focus to detect the solid and liquid materials, and they observe about the performance, the high accuracy, high key factor, high sensitivity and resolution, and high stability, and also for simultaneous measurement. So we can also design the microwave sensor to detect thickness, temperature, viscosity, solid and liquid for simultaneous measurement. And also we can develop the microwave sensor as a multifunctional device. So it can be used also as an antenna, filter, attenuator, copper, and etc. And also we can integrate the sensor using machine learning, active component, plasmonic sensor, and biological sensor. And this is the research gap and opportunity in our research. We focus to design the microwave sensor that has an independent sensing hotspot, so we can use to detect two different kind of materials under test. And also the advantages of the independent performance, we can use the microwave sensor also can be another device such as antenna, filter, and so on. So the planar sensor have several advantages, including the compact design, low cost, and high accuracy. And however, the sensor has a single function only to detect the permittivity of material under test. Thus, it will limit the function of the sensor and enable to fulfill the modern requirement. For example, we cannot connect or integrate the sensor with the Wi-Fi or IoT Zigbee. And then another constraint, there is still a limited number of sensing hotspot. Usually the researcher propose only one single sensing hotspot. So unable to support the simultaneous measurement. Okay, and then moreover, material characterization using microwave sensor is carried out by placing the material in the direct contact. So we also developed the microwave sensor for non-contact detection. Because if the material is direct contact with the sensing area of the sensor, it can reduce the performance of the sensor, because the surface of the sensor to be potentially damaged due to oxidation and corrosion. And this is the research gap opportunity. And this is my first project when I finished my PhD at UTM. We propose a dual band U-shaped resonator as an independent permittivity sensor. So we can see in here, the dual U-shaped resonator consists of the two pair of the U-shaped resonator connected with the T-stub transmission line that operate at FR1 1.29 GHz and FR2 2.01 GHz. So we can also analyze the S11 parameter based on the simulation. And after that, we can also analyze the concentration of the electric field based on the each resonance frequency. Based on the simulation, the electric field concentration of the resonator are at a different location based on their respective resonance frequency. We can see in here that for everyone, there are two potential locations. So we can try to put the sample in the A1 and A2. And for FR2, there are three potential locations based on the electric field concentration. So we can try to put the sample, and after that, we can analyze the correlation between the permittivity and the frequency. And this finding indicates that the two resonators work together to generate the resonance frequency of the resonator. Okay, and after that, after we design the resonator, we can also determine the sensing area and the potential location to place the sample under test. We can see in here, this is the E-field concentration from the FR1, 1.29 GHz, and this is the location of the electric field concentration from FR2, 2.01 GHz. Okay, and after that we can place we can put the samples based on the electric field concentration of each resonant frequency from the resonator. You can see this is the placement of sample under test. So after that, we can analyze the correlation between the resonant frequency and the permittivity. So in this case, we use non-permittivity material. So we can use permittivity from datasheet. As we know that RO580 has a permittivity of 2.2, FR4, 4.3. So we can use the general permittivity from datasheet, and after that, we can correlate the permittivity and the changes of resonant frequency of the resonator. So this is the measurement setup. We use the vector network analyzer and direct connect with the resonator using a coaxial cable. In this case, we use 3 different kind of metric under test. So for reference, we use in the vacuum condition, or the sensor is without a sample. So we can assume as a vacuum condition. Okay, this is the response of the frequency when we place the sample in the location of sensing area based on FR1. The resonant frequency moves to the lower, while for the FR2 is fixed. Also, in the same condition, we place the sample in the sensing hotspot of FR2 based on FR2, and the resonant frequency from FR2 moves to the lower, while for the FR1 is fixed. Okay, and then we can also correlate the permittivity correlation between permittivity and frequency using a simple polynomial equation, and after that we can calculate the permittivity based on this formula, this second order polynomial. And also this is for FR1 and this is for FR2. And we also analyze the sensitivity of the microwave sensor. We can see FR1 has a sensitivity about 9.1, and for the FR2 is 25. Why FR2 more higher than FR1? Because FR2 has using a high frequency. The frequency higher than FR1. So basically, based on our knowledge, if we use high frequency, the sensitivity also higher than the lower frequency. Okay, this is the performance of dual U-shape resonator as a microwave sensor. Finally, the permittivity measurement of first and the second resonator can be expressed in the mathematical model. So we can derive this mathematical model based on polynomial equation, and after that we can calculate the permittivity and compare with the datasheet permittivity to determine the accuracy. And after that we can compare with another works to show the novelty and the main contribution of our research. And this is the comparison with the existing work. We can see in here that our research as a main contribution, first the number of port. Usually the researcher only propose with 2 ports, and then they only propose 1 sensing hotspot. And in our research, we successfully designed the resonator with a single port with 2 different sensing hotspot. And another advantage is the resonator has also independent performance. So we can use to characterize 2 different kind material under test simultaneously. And this is my first project. And we continue to the another project. Okay, in this research, we integrate the microwave sensor and antenna sensor for contact and non-contact detection. So in the first project, the material still direct contact with the sensing area. So in a second project, we try to develop the sensor so it can be used for contact and non-contact detection. The sensor is developed using a dual T-shaped resonator. So same with the first project, we also analyze the location of the sensing area based on the electric field. This is the development model. This is the first resonator, and this is the combine of the first and the second resonator. So for the first resonator, the resonant frequency is only 2.35 gigahertz, and after we combine the first and the second resonator, the characteristic of the resonator as a dual band, as a dual band characteristic, that work at ever 1 2.35 and ever 2 1.57. So we can also analyze the electric field location based on the simulation using FSSS. For the ever 1, the maximum electric field is around the arms, and for the ever 2 is around both arms of the first and the second resonator. Okay, this is the sensing area determination and potential location. We can see from the simulation the concentration of the electric field of the second resonator within the open-ended stub, while the H field in the middle arm of the first resonator. Okay. On the other hand, the E field and the H field concentration of the first resonator with ever 1 2.35 in here were in the same location in the middle. So we also analyze the characteristic of the radiation pattern, and based on the simulation, the radiation of the E field and the H field from ever 1 is about 10 dB, okay, and while for ever 2 is around 1 dB. The simulation radiation pattern of the E field and H field, both resonators show the first resonator had the maximum radiation. So based on this simulation, we can assume that the first resonator represent ever 1 2.35 gigahertz can be used for antenna sensor, then can be utilized for non-contact detection. And we also propose a scenario for contact and non-contact detection, also same with the first project. And in here we can see this is for contact detection. This is for contact detection. We can see this is the response of the resonant frequency. When we place the material in the contact detection, the FR2 move to the lower, while for the FR1 almost fixed. Okay, this is the scenario. The scenario 1, the first resonator we place in the vacuum condition, and for the second resonator, direct contact without air gap. And this is for the second scenario. The second scenario, the first resonator is we place the material with non-contact condition using air gap 0.5, and the second resonator in the vacuum condition. And this is the correlation between permittivity and ever 1 and ever 2. We can see in the scenario 1, okay, the ever 1 almost fixed, while for the ever 2 move to the lower, in line with the increasing permittivity. And also we can see this for the scenario 2, ever 2 almost fixed, for the ever 1 move to the lower. We can see in here that the ever 1 is more sensitive than ever 2 is more sensitive than ever 1. This is for contact detection. This is for non-contact detection. Okay, this is the fabrication of our sensor. We use FF4 substrate, and then after that, we also compare the simulation and the measurement in our laboratory. And when we do the measurement, we use also same scenario with the simulation. And this is the performance of our sensor. We can see FR2 move to the lower, and in for non-contact, FR1 also move to the lower, while for another frequency remain fixed. Okay, and this is the correlation, also same with the simulation, the correlation between FR1 and FR2 when we use as a contact and non-contact detection microsensor. And for contact detection using microsensor, FR2 shift 1.81 gigahertz until 1.69 gigahertz, while for FR2 shift slightly 2.34 until 2.32 gigahertz. And furthermore, for the antenna sensor, also shift 2.309 until 2.28 gigahertz, while for the FR2 shift slightly 1.8 until 1.807 until 1.804 gigahertz. And we also analyze the sensitivity and the delta F of the contact and non-contact detection. And the maximum sensitivity of the antenna sensor, we use 0.5 millimeter until 1.5 millimeter to observe the sensitivity for non-contact detection. Were in the range 0.001 gigahertz until 0.02 gigahertz and 0.39 megahertz until 4.24 megahertz. So we can see in here. We also analyze the ideal distance for the non-contact. So we can see in here, if we place the sample in the minimum distance, so the sensor is more sensitive. So 0.5, 1.5, and 3 millimeters. And then after that, we also develop microwave sensor based on dual T-shape integrated with antenna. So in the second project, we only propose the microwave sensor, antenna sensor for contact and non-contact detection. And in this project, we combine microwave sensor with independent performance, and also can be used for antenna and to transfer measurement data using access point. So we can see in here, this is the structure of the multi-case code T-shaped resonator, and this is the development model, the first step, second step, and the third step. So we propose 3 different resonant frequency. FR1 as an antenna, FR2 and FR3 we use as the microwave sensor. So all of the resonant frequency has an independent performance. So we can use FR2 and FR3 as a microwave sensor, also has independent performance, and FR1 in the resonant frequency of 2.46 gigahertz as an antenna. Okay, this is the sensing area determination and potential location. We also use same technique. We analyze the location between the maximum E field and the maximum H field. And the maximum electromagnetic wave radiation was only generated from the first resonator, which operated at the resonant frequency 2.46 gigahertz. So this is the scenario when we place the sample. So the first sample we place in the second resonator, and the second sample we place in the third resonator, and the first resonator we propose as an antenna. And we also analyze the radiation pattern of the resonator in based on each resonant frequency. We can see in here that the first resonator could be used as an antenna according to the performance of the radiation pattern obtained from the simulation, while for the second resonator and third resonator could be used as permittivity sensor. Why? Because the first resonator has a high radiation if we compare with the FR2 and FR3. Okay, and this is the measurement setup. We also using vector network analyzer to analyze the performance of the resonator based on the resonant frequency and scattering parameter S11. And we also propose 2 different scenarios. So in the second project, we only use a dual band characteristic. So in this case, we use triple band. Okay? So the first resonator, we only use as an antenna. And the second and the third resonator we use as a microwave sensor that has independent characteristic. So this is the measurement result of our sensor. We can see in here, FR1 is fixed, FR2 is fixed, and FR3 is fixed when we change the sample in the material B. So, and this is for the scenario 2. When we change the sample in the material A, RO580, RO4003C, FR4, and RO3006, the resonant frequency of the resonator moves to the lower, while for the FR1 and 3 is fixed. Okay, and this is the correlation between each resonant frequency and the permittivity. In scenario 1, FR3 shift to a lower frequency. You can see in here, move to the lower frequency in line with the change in permittivity of the material under test, while for the FR1 and FR2 remain fixed. Okay, and similarly, the reflection coefficient FR1 and FR2 are also fixed, because the material base of the resonator is fixed. So in this case, we also use the fixed sample test using RO 5.0. And then for the scenario 2, okay, when we change the random material under test, FR2 shift to a low frequency. You can see in here, it moves to the low frequency, and FR1 and FR2 were fixed in line with the reflection coefficient. And moreover, the radiation pattern from antenna during scenario 1 was fixed in scenario 2, and the radiation pattern from antenna changed slightly. You can see in here, this is for the scenario 1 and this is for the scenario 2. And we also analyze the sensing performance in the antenna performance in our anechoic chamber. You can see this is the radiation pattern from the simulation and the measurement. And this is the calculated comparison between calculated and reference permittivity. Also, we use polynomial equation, second order polynomial equation. You can see in here that the polynomial equation has a high accuracy with the R square of 1. And we also implement the sensor to transfer the data using access point. You can see in here, this is the scenario. We use the access point, and then we connected the proposed device with the coaxial cable and direct connect with the USB Wi-Fi, and then we try to transfer the data from the PC, and then we transfer using access point with the distance of 60 cm. Okay, and we also analyze the S21. We can see in here that the S21 of the FR1 is more higher than FR2 and FR3. So this result indicate the FR1 also can be function as an antenna to transfer the data. And this is the performance of the transfer and receive data after we try to transfer the measurement data using antenna, right? Microwave sensor as an antenna, and then we analyze using access point. And this is the development model of our sensor. In this case, we use the IDC and T-shape. So the interdigital capacitor was introduced to enhance the electric field of the microwave sensor. So in this case, we can use two different parameters. We can use a sensor for near field detection and far field. For near field, we can use S11 parameter, and then for far field, we can use interrogator antenna to detect the permittivity of materials based on a shifting of resonant frequency. And this is the scenario for permittivity detection. You can see in here, we use the proposed device, and then we also use the interrogator antenna with several distance. And then after that, we can also use IDC as a contact detection, and we analyze using S11 parameter. Okay, and then we also analyze the E field and the H field of the microwave sensor, okay, using a simulation based on HFSS, and the sensor work at the two different resonant frequency, 2.32 and 1.52 gigahertz. And this is the structure of our sensor, and this is the development model. We also use same technique. We analyze based on the electric field and the H field. We can see in the FR1, 2.32 gigahertz, the electric field and the H field of the T-shaped resonator is in the middle arm of the resonator. And for the second resonant frequency, FR2 1.52 gigahertz, the maximum electric field is in the gap of the IDC. So we can use in here to detect the permittivity for near field detection. And in here we can use interrogator antenna to detect permittivity based on far field region. So this is the comparison between the simulation and the measurement. We also using a portable VNA. So we use interrogator antenna with a distance 10 cm, and we place the sample based on sensing area that we determine based on the simulation using SFSS. And we also use non-permittivity material RO580, RO4003, FR4, RO3006, and also with the same dimension 10 cross 10 with the thickness of 1.6 millimeter. And after that, this is the result of our sensor for far field region. Using interrogator antenna, we can detect the change in the permittivity represented by shift of resonant frequency. We can use interrogator antenna in the same frequency, so we can analyze the permittivity based on shift of resonant frequency. And this is for the near field region. We can use S11. We can see in here FR2 move to lower in line with the increasing permittivity of the materials. And this is our last project. We also develop a single port microwave sensor based on IDC. Okay, so we focus to enhance the IDC performance, and after that we try to observe the stability of microwave sensor by place the copper shield in the upper of the resonator, and this is the equivalent circuit, and this is the comparison between the finite element modeling and equivalent circuit, and this is the performance. So based on our research, the accuracy of the sensor is more stable. If we use IDC sensor, even we place the copper shield in the top of the single port. As we know, if we put anything, copper shield or another materials in the top of the antenna, the resonant frequency also change. So in this research, we focus to propose high stability microwave sensor based on IDC structure. And this is the structure of our sensor. We use the IDC and using a dual branch line. This is the first fit and this is for second fit to develop dual band characteristic of resonator. And we also analyze the electric field. We can see in here, the electric field is more confined in the IDC structure, but the electric field, the H field in the IDC is low. Well, for electric field is higher than the H field. So we can use this area to place the sample, and after that we try to analyze the stability by add copper shield in the top of the sensor. So this is the measurement result. We can see in here, this is the simulation and measurement, comparison simulation and measurement. And this is the performance of the resonator when we place the shield, copper shield, 1.5 to 0.5 centimeter. And after that, we can see there are no significant effect. There are no significant effect when we place the copper shield in the top of the resonator. And we also analyze the performance of the sensor while we control the distance between the sensor and the copper shield. This is for the 1 cm, this is for 1.5 cm, this is for the 2.5 cm. And after that, we also analyze the frequency detection resolution and the accuracy. And based on our result, our measurement, the copper shield has an effect to accuracy and also for FDR. But based on measurement result, the sensor has stability both with and without disturbance. With the range of the frequency detection resolution 0.009 until 0.4 gigahertz, and the accuracy is still okay between 90 until 95% for both resonant frequency. So IDC, based on my experience, IDC is more powerful structure if we want to design the microwave sensor. So the electric field more concentrate, so there is low lah for noise. So we can use the IDC structure to enhance the performance of the microwave sensor. And this is the concluding remarks. Based on our research, a compact integrated microwave sensor and antenna was successfully designed and validated. The system achieved dual functionality, so we can use the microwave sensor and antenna simultaneously. And the resonant frequency shift effectively indicate the electric property variation as of tested sample. And the proposed sensor has demonstrated high sensitivity and stable radiation performance within 1.1 until 3 GHz range. And simulation experimental result confirm strong correlation between sensing response and material permittivity. And integration enhance practically flexibility and real-time monitoring capability. And other significant potential for smart material monitoring, industrial automation, and IoT-based sensing application. And this is the future potential works, maybe for the PhD student or master. We can develop the microwave sensor. For example, multifunctional and independent microwave sensor. So we can use the sensor also as an antenna and integrated with the IoT, Wi-Fi, and Zigbee. Therefore, the recommendation for future work to implement the sensor and antenna simultaneously for real-time measurement. And another potential work, we can also use the microwave sensor to detect a different kind of materials. For example, low permittivity maybe for solid materials and high permittivity maybe for liquid or another materials. So if the sensor has independent characteristics, so it can be used for different sample simultaneously. So we can also use as a differential sensor. So we can also analyze the difference between material A and material B. Okay, and another potential work, we can also integrate the sensor with the active component such as transistor, diode. Okay, so we can improve the performance such as electric field and the sensitivity of the sensor, and we can also integrate the sensor with the machine learning, so it can predict the permittivity of the sample and improve the accuracy. Okay, this is my short journey. I continue my PhD in 2021 and finish in 2024 at the University Technical Malacca, and we also publish 3 Q1 journal on IEEE sensor, 2 publication, and the measurement 1 publication, and we also publish our research into conference. And this is my supervisor and my team. Okay, so I continue my PhD under supervised Prof. Zahril Adha Zakaria and Dr. Nur Azwan Sairi. And this is the milestone publication. We also publish several publications in IEEE, measurement, and peer. And this is the milestone grant and collaboration. We also collaborate with other university such as ITEM, Universitas Sultan Agung Tirtayasa, Mercu Buana, Universitas Riau, Polytechnic Nans, ITB, and also IPB. And we also achieve a grant from Ministry of Higher Education in Indonesia and award by IEEE for best paper and another recognition. Okay, I think that's all from me. Thank you for your attention. Terima kasih. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Associate Prof. Dr. Shah Alam, for the excellent presentation and for sharing your innovative research contributions. So, any questions from the floor? Okay, so we have question from the online session.
Okay,
Okay.
thank you. Maybe I check my asking my question in this chat. okay, I want to talk. Thank you for Mr. Alam because your presentation. I want to know about the range of frequency because I saw that your presentation, your frequency is 1 until 3, and maybe the one or the presentation your research is 1 until 6. I want to know, have you designed or measure about the antenna as the sensor upper 6 gigahertz working frequency, and why you choose 1 until 3 gigahertz? Okay, thank you.
Okay, thank you for the question. First, why we choose the low resonant frequency? Why we choose? First, if you want to detect specific about the characteristic, it's better you use low frequency. Okay, this is based on my experience. But if you want to detect specific location, maybe for hole detection or maybe for crack detection, you can use a higher frequency. So the low frequency, for example, 1 until gigahertz, we can use for fabrication is more simple. Especially if we fabricate using FR4 substrate, it's more simple for us to fabricate. And then a second, we don't need the higher vector network analyzer. So as we know, the vector network analyzer is very expensive. If we use maybe for 6 until 12 gigahertz is very expensive. So we can use 1 until gigahertz only to detect the permittivity or maybe permeability. It's okay. There is no problem if we use 1 until a gigahertz. Okay, this is based on my experience. But if you want to detect maybe for the location, so I read some paper. There are researchers to propose a microwave sensor to detect hole detection, to detect crack detection. So you cannot use 1 until gigahertz. This is based on my experience. Yeah. You better choose maybe higher frequency. So I think when we do our research, we must also compare with another researcher, and we must tune our research with the equipment that we need and that we have in our laboratory. So in our laboratory, we only have 1 until 6 gigahertz for vector network analyzer. So why we choose 1 until 3 gigahertz? Because we only have VNA 1 until 6 gigahertz. So we try to explore more specific about the microwave sensor in range frequency 1 until 6 gigahertz. But if you want to use the high frequency, is better. I think if you want to detect crack or hole detection or maybe breast cancer detection, I think it's more suitable if you use the high frequency. Okay, thank you.
Okay, thank you for your answer.
Okay, thank you for the question. Any other question from the floor? I have questions. What is the key challenge that you should be aware when attempting to integrate the sensor and the data transmission into single device?
Okay, can you repeat your question?
What is the challenge
Okay,
that
what the challenge? Okay.
when
Okay.
integrating the sensors and the data transmission into single device?
Okay, I think the challenge is we can design the micro sensor with the independent performance, so we can use as an antenna and a micro sensor simultaneously. But the challenge we need more detailed research how to switch the function of antenna and the microsensor. So basically, when we design the microsensor, we only use for material characterization, and after that, after we finish the measure and determine the permittivity, we can change the function of the resonator as an antenna. So the main challenge is how to switch the functionality of the antenna and the microwave sensor. So we need another device, or maybe we can also modulate it. The signal from the microwave sensor can be modulated in the antenna, so it can be transferred simultaneously. I think that's the main challenge when we integrated the microwave sensor and the antenna.
Okay, thank you. Okay, maybe the final question from the chat box from Mr. Udin. He asking what is the distance between transmitting and receiving antennas? If there is CPW implementation, is there any change in the gain, SAR, and others?
Okay, it's very good question. So basically, if we design the antenna, when we do the measurement in an echo chamber, we use a far field region based on the Fresnel region. So if we use the sensor in the specific area, maybe in the outdoor condition, the gain and the performance of antenna also degrades. So it's important for us to enhance performance of the antenna. Also, in this case, we only focus to integrate integrate microwave sensor and antenna. So maybe in the future work we can also enhance the performance of antenna. So one of my students also do the research to enhance the performance of antenna, and after that we can integrate the antenna with the microwave sensor. Okay, so it's true, if we use the antenna in the outdoor condition, the gain, the radiation pattern, and also the resonance frequency also change. Okay, that's another constraint. So maybe we can also develop or also enhance the performance of the antenna when we integrate with the microsensor. I think that's all for me.
Okay, thank you, Associate Prof. Dr. Shah Alam. Before we end our morning session, I would like to invite everyone to join us for AP Technical Meeting Series 1 2026 that will be held on February next year at Faculty of Electrical and Electronic Engineering and Technology FTKA at University Technical Malaysia, UTEM. So the topic will be focused on microwave technology and applications. Please scan these QR codes for research presentation and registration. Now, thank you for your attention and energy for this morning session. Let's take a break and we will continue the afternoon session at 2 p.m. Thank you, everyone. Okay, for the physical attendees, you can have lunch at the outside.